Good morning, friends. I don't see many people have joined today. I don't know what is the reason. Is it the minor exam or anything else? Any guess? Or did you have a previous lecture which kind of overrun its time?
So it's minor only.
Minor exam.
Yes,
Because
sir.
studying.
Fine, fine. Okay, fine. Okay, I hope people watch this lecture offline at least. Cool. Okay. So let us resume where we left off in the last class. Right. So we were looking at this bipartite matching problem. We thought of the left hand side as left hand side of vertices, which we call, let's say, V1 as the set of students, and the right hand side of vertices, the set V2, we thought of them as hostel rooms. Well, the sizes need not be equal, although I have drawn that way in this diagram. Right. And then we were asking the question, when does there not exist a way uh, to assign a room to every student, right? So we are talking about one-sided thing. We want every student to get a room. We are not worried about whether every room is occupied or not. Right. And then we said that, okay, if you have this kind of structure where you have a larger set of students who is interested in a smaller set of rooms, then this is just impossible. Okay, so we made this observation, and then the question we asked is this condition sufficient? Okay. So suppose it is guaranteed that in your bipartite graph, for every subset of vertices on the left hand side, its kind of neighborhood is no smaller than the set itself. Then does that guarantee the existence of a matching which will match all vertices in V1? Right. So this is the question we'll try to answer in the previous in the let's say hopefully the first half of the lecture. Okay, so let us set up some notation over here. So definition, or rather, let me not call it definition. This is some notation. Notation if G is VE is a bipartite graph. V1, V2 is a bipartition of G. Okay. Let G be a bipartite graph and let V1, V2 be a bipartition of G. So for a subset S, which is a subset of V1, define, right? So N of S is just the so-called neighborhood of S. N of S is the set of all V in V2 such that for which there exists some U in V1 such that UV is an H. Okay, so if this is your S, then this is your NS, right? The set of, right? So if S is some subset of students, N of S is the set of rooms with the property that at least one student is interested in that room. It's the set of all rooms such that for every, right? So a room is in NS if and only if there exists some student in S who is willing to take up that room. Okay, and now observation. The observation we had was if there is a subset S on the of V1 such that the size of S is strictly greater than the size of N of S, then there does not exist a matching which matches all vertices in V1. Okay, obviously you can flip this condition around and say that if there is a subset of vertices S of V2 such that its neighborhood is strictly smaller than itself, then there does not exist a matching which matches all vertices in V2. Right? So you can just flip the argument around. But let's just worry about the one-sided argument. Okay, so now the question is this condition sufficient? Is this condition sufficient? Is this condition necessary and sufficient? Right, so in other words, we are saying that if, right, so we are asking two kind of equivalent questions. If the graph has a matching which matches all of V1, right, so that obviously guarantees that the size of S is less than or equal to size of NS for all S. But conversely, if the graph does not have a matching which matches all of V1, can you actually find an S such that the size of S is strictly larger than the size of NS, right? So that is, if there does not exist a
Excuse me, sir.
matching. Yeah. Yes, Abhinav. Abhinav, go on. Abhinav, we can't hear you. Am I audible in the first place? Because I'm not sure whether Abhinav is able to hear me. Could somebody
You're
confirm
audible.
whether I'm audible?
You're audible.
Okay, Abhinav, your hand is up. I'm not able to hear you. You are muted. I guess that is the reason. Okay, I'm not sure what is the issue on Abhinav's end. Abhinav, if you are able to hear me, if you have some issue from your end, you can just ping me after the lecture. Okay, fine. So let's move on. So if there does not exist a matching which matches all of V1, does there necessarily exist a set exist as subset of V1 such that the neighborhood of S, the size of S is strictly greater than the size of the neighborhood of S. Okay. And somebody, I think somebody mentioned in the last class that, okay, this looks like a necessary and sufficient condition. So somebody believed that the answer to this question is yes. Who was it? Could they raise their hand? I think somebody said it. Okay, possibly they're not present today. Fine. Okay, so turns out, okay, I think Abhinav has sent something. You should belong to S, right? Oh, yeah. Good point. Sorry. Yeah, my bad. Thanks, Abhinav. Right, so we are talking about neighborhood of S. So we are looking at all V in V2 so for which there exists a U in S such that U is a neighbor of V. Yeah. Okay. Okay, is everybody with me up to this point? Right, so we'll try to prove that this is indeed the case, that if there is no matching which matches all of V1, then actually there exists a set S, subset of V1, whose neighborhood is strictly smaller than itself. Okay, and this result is called Hall's theorem. Okay, so let us put down the statement of the theorem. Let G equal to VE be a bipartite graph with bipartition V1, V2. Okay, what is the matter? V1, V2. Okay, right. So then the claim is that there there does not exist matching in G that matches all of V1, right? If and only if, what happens? Remember, this is an if and only if. If and only if there exists a subset S of V1 such that the size of S is strictly less than the size of NS. Okay, so one direction of the proof is easy. Which direction is easy? If is easy or only if is easy? Come on, somebody.
If
If is easy. If there exists S subset of V1 such that size of S is less than size of NS. Oh, did I put the wrong sign? Greater than, no? Greater than, yes. Yeah, if there exists such a subset, then there is no matching which matches all of V1. Okay. So if yeah, Arun, yes.
Nothing.
Okay, fine. Yeah, so right to left direction is easy. So let me just write in one sentence. So this follows by pigeonhole principle. Right, so think of students as pigeons and hostel rooms as holes. So you're trying to put a larger set of pigeons into a smaller set of holes. So obviously you'll have to put more than one pigeon in some hole. Okay, fine. Maybe you should call it student hostel room principle if you like, instead of pigeonhole principle. Okay, anyway, fine. So what about the left to right side? Right, so what do we want to prove? Suppose there does not exist a matching in G that matches all of V1. Now we want to prove there exists a set S such that something happens, right? There exists. What proof strategy should we use? What proof strategy becomes immediate?
So contradiction or contrapositive?
Construction. We'll use proof by construction. Okay. Proof by construction. Right, so how do you construct the set S? So let M star be a max size matching in G. Start with a maximum cardinality matching in G. We know that there must exist a vertex which M star does not match. Right, that is what is given to us. There does not exist a matching in G that matches all of V1. Right, so therefore in particular M star is going to leave some vertex in V1 unmatched. Right, so let's draw a diagram maybe. Right, so this is your V1, this is your V2. Right, so M star is going to leave some vertex over here unmatched, right? So M star could be something like this. This is your M star, let's say. Right, so this is M star. And it's going to leave at least one vertex unmatched. Okay, so let's call this vertex something. No, let's call this R. Let R be R in V1, be an arbitrary vertex left unmatched by M star. Okay, take any one, that's good enough. Okay, so now what do we have, right? So this M star is a maximum cardinality matching. So what does that tell us about augmenting paths?
there isn't one.
There isn't any augmenting path, right? Which means, right? So how will an augmenting path, if it exists, would look like? It will start from some vertex in V1, let's say. It will alternate between the matching and non-matching edges, and it will end in a vertex in V2. Right? So now we have this unmatched vertex in V1. So let us look at all the alternating paths starting from V1. And we know that none of them is an augmenting path. Okay, so we'll look at all possible alternating paths starting from R, right? Which means that their first edge is necessarily not in M star because R is not matched under M star. First is edge is necessarily not in M star, second edge is necessarily M star, third is not in M star, fourth is in M star, and so on. Okay, right? So what am I trying to do? So M star is a maximum matching, but I'm kind of trying by brute force to find an augmenting path. And now I want to see where do I fail in trying to in my attempt to find an augmenting path. Right? So I'm starting from R and I'm just trying to find augmenting path. Right? But I know I'm going to fail, but where will I fail exactly? Right? So what I'll actually get is I'll get a set of alternating paths which kind of end somewhere without being able to be completely transformed into an augmenting path. Okay, so where will they end? Right, so where will they end? Right, so how will an alternating path from R look like? So your first edge is going to be unmatched, then the second edge is going to be matched, then the third edge is going to be unmatched, and so on and so on, and then it will end somewhere, right? Something will happen and eventually it will end in a matched edge, right? When will this happen? It will happen when all the neighbors of this guy, are vertices in the alternating path itself, right? Which is why this you are not going to make any progress from this point in your attempt to find an augmenting path from this point. Okay, is the idea clear or should I repeat? I am trying to find an augmenting path starting from R. Right, I'm just trying to extend until I fail, until I just cannot add one more edge to the add one more vertex to the augmenting to my constructed alternating path. Okay, and when will that happen? Well, it will not happen. It will not happen if I'm currently at in a vertex in V2. Okay, where is my mouse pointer? Achha, okay. Yeah, so this attempt to extend my alternating path is not going to fail while I'm at a vertex over here. Why? Because if I'm over here, right, two things are going to happen. If this vertex is unmatched, then I have found an augmenting path, which is a contradiction. So therefore, this vertex must be matched, and it must be matched to some vertex which is other than whatever I have found so far. Right, so if I'm currently in my attempt to find an augmenting path, if I'm currently at a vertex in V2, right, I know that there is no augmenting path, but then that implies that I can extend my current alternating path to get to a vertex on the left hand side. Is this point clear?
Yes, sir.
Okay.
Yes, sir.
Yeah. So now, therefore, my attempt is going to necessarily fail while I am at some vertex in the left hand side. Okay. So let us look at all of these vertices kind of which I'm able to reach from this R using alternating path, right? So let S, so I'm going to call that set S. Let S be the set S subset of V1 be the set of vertices that are reachable by alternating paths starting from V1. Yeah, Shrimanti, your hand is up. Shrimanti?
Sir, in this, yes, sir. So here, when we say that we cannot have, like we have to end in a vertex in V1, then can we argue by that even length paths, all paths have to be even length? That is why.
All paths have to be even length. Be careful about what exactly you're saying.
I mean, in a connected component, the paths which are part of the maximum matching, they have to be.
Paths are never part of a maximum matching. You're talking about alternating paths of M star?
Yes, sir.
So alternating paths of M star are of even length. That is a true statement. Yeah.
So then how did we argue that?
Well, not necessarily, right? Not necessarily. Technically, Shrimanti, what could happen is you have, let's say, two matching edges, and there is one unmatched, non-matching edge between them. So this is an alternating path, but it's an odd length alternating path, but it's not an augmenting path. Okay, so what you said is not really true. Do you get it?
Yes.
All we know is that there is no augmenting path. That's all. Okay. Right.
So can you repeat the argument why it should end in V1?
So if your alternating path ends in V2, what does that mean, right? Right. So you are okay. Let me draw a different diagram. You're kind of trying to get an alternating path, and it ends in V2. Right. So let us ask the question: who are the neighbors of this guy? Right. So let's call this V. Let's call this R. Who are the neighbors of V? Right. One possibility why. Okay. By the way, when you have reached V, you know that this edge is not in M. Right, Shrimanti?
Yes, sir.
Yeah. So you know that this edge is not in M. So if you want to extend this alternating path further, you need to take an edge in M necessarily. Okay. And now you are saying that you are not able to take an edge in M. What does that mean? It means that V is an unmatched vertex. Well, V cannot be matched to any of these, right? Because every time you are taking, right? So every time this guy is traversed, the earlier right? Yeah. When you visit on the vertex on the left hand side, except for this R, the previous vertex is its partner, right? So and the vertex cannot have two partners.
Yes.
Right. So therefore, this such an edge cannot be in M. Right. So what does that mean? V does not have a right. V does not have a partner, and that is a contradiction because this is an augmenting path in that case. Right. R does not have a partner. V does not have a partner, and you have an alternating path between them.
Got it, sir.
Okay. So that would be a contradiction to the maximality of M star. Good. Okay, so fine, that are reachable by alternating paths starting from V1. Okay, good. Right. So this is my S, and now I want to claim that this S satisfies this condition. Right. So the size of the neighborhood of S is less than the size of S. Right. So again, just to get yeah. Yes, Abhinav.
So can we start from any point of V1, like starting from R of V1 or any point of V1?
Yes. So what is R after all? R is an arbitrary vertex in V1, right? Which is left unmatched.
Yes.
Choose whatever.
So we should start from an unmatched what here R, right?
Yeah, some unmatched vertex. Okay. So technically, even if you take a set of unmatched vertex and you start from that set, still this proof is going to work. Just for the sake of simplicity, I took one unmatched vertex and then I wrote down the construction. Okay. Yeah. Cool. Right.
So
Yeah.
S here is any a vertex that is reachable from any alternating path. So,
But from R.
Okay.
Okay. So there should exist an alternating path from R to that vertex. Only then you'll include it in V1. Sorry, in S. Okay. So now what is the neighborhood of S? Let's try to understand the neighborhood of S. Okay. So how do we understand the neighborhood of S? Right. So I want to claim that. That the neighborhood of S is the set of all V in V2 such that there exists an alternating path from R to V. Right, so I'm applying the same condition except that now I'm applying it to V2 and I claim that out of this I'll precisely get the neighborhood of S. Okay. Okay. So why is this so? So let's prove this claim first. So let's keep this proof on stack, incomplete on stack, right? So what is the proof of this claim? Right. So if what happens, right? So suppose V is in an S, then right, then what happens? Then there exists some U in S such that UV is an H, right? But because there is right, so yeah, so because U is in S, so but then since U is in S, U is in S. What does that mean? What is the definition of S? So that says that there exists an alternating path from R to U. Okay, what are we trying to prove? If V is in NS, I'm trying to prove that there exists an alternating path from R to V. And conversely, I'll prove that if there exists an alternating path from R to V, then V must be in NS. Okay, so now yeah, so you right, so now if right, so if UV is an edge of the matching, right, there are two possibilities. Either this edge is in the matching M star or it is not in the matching M star. If it is in the matching M star, then what happens? What can you say about V? Right, there is an alternating path from R to U and U is matched to V. What can you say about V? Right, so observe. Yeah, yes, who is this?
So that
Vishal?
just means there's an alternating path, right? By
Yeah,
definition.
yeah, yeah. Right, so how, right, so remember in that alternating path, whenever you go from V1 to V2, you are taking a non-matching edge. And whenever you are going from V2 to V1, you are taking a matching edge. Right, so remember, where is U? U is somewhere over here. And you have an alternating path from R to U. So what should the last edge of the alternating path be? Should it be in V or in M star, or should it not be in M star? Right, so every edge which you are taking to go from V1 to V2 is a non-matching edge, and every edge which you are taking to go from V2 to V1 is a matching edge, no? Okay, so I am having a feeling that some of you are lost. So raise your hand if you are completely lost at this point of time. Okay, Aniruddha is lost. Okay,
Sir, I
fine.
kind of get it, but can you actually draw a concrete example rather than just
I see.
these?
Okay, sure. Sachit, any specific question you have?
Like it feels intuitively right, but still I'm not able to follow.
Okay. Abhinav, your hand is still up.
So my doubt is that you said let S be V1 and belongs to V1 be a set of vertices that are reachable by alternating paths starting from V1. So shouldn't it be R here? Starting from
Sorry,
R.
R.
I'm
Is that
getting
the reason
confused.
behind the confusion? Is that the reason behind the confusion?
Yeah, for me it was the confusion. For
Yeah,
me
what
it
about
was.
the others? What about the others? Right, I'm interested in only in alternating paths starting from R. Sorry for that mess up. Okay, so what are we saying? If you look at this diagram, so how will an alternating path look like? From R, you will take a non-matching edge. Could be any of these, could be several possibilities. But then as soon as you go into V2, you are forced to take a matching edge to come back to V1. Right? Once you come back to V1, you have lots of choices for non-matching edges possibly. But once you go to V2, you are forced to take a matching edge to come back to V1. Right? That is how an alternating path is going to look like. Now is it clear?
Yes, sir.
Yeah. So now what does that mean? If UV.
So that means we have to.
Yeah, go on, Abhinav.
So do we say that whenever this alternating path starts, it either stops. It either stops in a point in V1 which is already matched, or in a point V2 which is not matched.
The claim is it cannot stop in the point in V2 which is not matched. Otherwise it would be an augmenting path.
That we can contradict later. But these are the only two possibilities.
Yeah. Fine. Yes, you're right.
Okay.
Yeah. Okay, so now what does that mean? What can you say about this edge, right? So it is in the matching, right? So U is a vertex that is reachable from R. Look at that alternating path from R to U. The last edge must be a matching edge. Last edge traversed by this path must be a matching edge, and therefore it must precisely be this, because this is the only matching edge which is incident on U, right? So what does that mean? So therefore, right, so let me just write the claim and then let's see whether people are convinced or not. So then V is the second last vertex in every alternating path from R to U. Right? Any alternating path from R to U, because R and U are on the same side, must end in a matching edge. And the only matching edge incident on U on V is this edge UV. Incident on U is this edge UV. Right? So therefore that must be the last edge traversed, which means that V must be the second last vertex in any alternating path from R to U. Is that okay?
Sir, like for example, on the diagram, if I take the second dot from the top, so that can belong to NS, right?
This one?
On the right side, on the right side.
This one? Yes.
Yes, sir.
Yeah.
So here, what is U for this particular V?
Okay, wait. So what is your, okay, hold on. So V is in NS.
UV not in
hold
the
on.
matching.
Sorry?
UV should not be in the matching, right? Rather than being in it.
Okay, did I mess up something? Hold on. Let's see what I wrote. Then there exists U in V such that UV is in E. Since U is in S. Okay, so your question is what will be the U for this guy, right?
Yes, sir. I think that it should not be in the matching UV. That I was getting.
That is the other case. Right? So if UV is in the matching, what happens? If UV is not in the matching, something else happens. Right? Which is why there will be an alternating path from R to V. Right? So if what happens? If UV is not in the matching, right? So then what do you do? So then right? So you right? So then right? So unless right? So then the alternating path from R to U, right, can be appended with, so V can be appended to the alternating path. To the alternating path from R to U, right, unless V is already, right, unless V is already in the path. Right, so if V is already in the R to U path somewhere, then there is nothing to prove, because every kind of prefix of the alternating path is also going to be an alternating path. But if V is not already on the path, what can you say? Take the alternating path from R to U and just append V to it. That will be an alternating path from R to V. Is this point clear?
Sir, please explain this again.
Yeah. right? So you have, right? So you have an alternating path from R to U, right? So this R, this is U, right? So if V is already on this path, then you already have an alternating path from R to V. Right? So is it okay? First of all, is it clear that any prefix of an alternating path is an alternating path? Raise your hand if this itself is not clear. Right, so that seems clear to everybody. So right, so if V is already on the path, then you'll just take the prefix until V. That will be an alternating path from R to V. But if V is not on the path, V is somewhere else, I can just take this alternating path that ends in the matching edge, right? And I can just append V to that alternating path to get another alternating path from R to V.
Yes, sir, got it.
Okay. Any issues with this? Raise your hand. Feel free to ask. Yes, Anirudh.
Small clarification: is a single edge an alternating path?
Is a single edge an alternating path? You are talking about specifically path starting from R?
Yes. So if
Yeah, it would
that
be an
first
alternating
one.
path. It would be an alternating path, of course. Yes.
Okay.
Right. Okay. So cool. Right. So this part is clear. If some vertex belongs to NS, then it belongs to this set. And now conversely, if some vertex belongs, if there is an alternating path from R to some vertex V on in V2, right? So then that's trivial, no? Right. So if conversely, if there exists an alternating path from R to V, where V is in V2, what do we have, right? So let U be the second last vertex on this path. Possibly U is equal to R on this path, right? So then what? Then U is in S, right? Because if I just chop off the last edge of this alternating path, I'll still get an alternating path, and that will be an alternating path from U R to U. So therefore U is in S, and therefore, right, because V is a neighbor of U, therefore V is in S. V is in N of S. Okay, raise your hand if there is any question. Okay, was this too fast? Bit too fast?
Sir, I was a bit disconnected in between. So, like, can you just please explain, like, that we wrote that since U belongs to S, there exists an alternating path from R to U. So, like, maybe I'm losing, like, forgetting something or something like that. But can you explain how this is true?
What is the definition of U? What is the definition of S? Sorry, what is the definition of S?
Like,
Right, this is the definition of S, no?
yeah, okay, sir, okay.
Okay,
I lost this.
that is just by the definition. Anything else? Let me actually pause for a couple of seconds and then let you stare at the slide. Okay, so what did
Sir,
we
why
prove?
did we?
Yeah. Yes, Rimandi.
Sir, why did we say? Sir, why did we say conversely? Like these are both the same parts, right? Because we are saying
Conversely,
that.
okay. Okay, so okay, right. So I interpreted this equality as saying that if U belongs to NS, sorry, U belongs to V belongs to NS if and only if V belongs to this set. Right, so that's why I kind of said conversely. Earlier I proved that if V belongs to NS, then V belongs to the set on the right hand side, and now I'm trying to prove that if V belongs to the set on the right hand side, then V belongs to NFS.
Okay, okay, sir.
Okay. Right. So now, yeah.
So like just to confirm, what we have done is first we started from R, and then by alternating paths we tried to reach to some vertex on V1. All such vertices we called part of the set S. Then
Yes.
if we created a set where we are through alternating paths we are trying to reach to V2, and all those vertices we called NS. Then we showed like all the vertices on that on like all those set of vertices we proved that those vertices are NS actually. Like
Yeah,
there
exactly.
exists NS from the previous set to this set always for some
Correct.
vertices.
Right.
Okay.
Yes, absolutely. You're right, Chinmay. Yeah, Chinmay is right. Okay, so
that
now
should
what?
be M star in the if UV does not belong to M star.
M star. M star. Yeah, that's the only matching we are talking about. So yes, M star, obviously. Cool. Thanks. Okay. So now what? So now let us. What does that tell us? Now, how can we claim that size of NS is strictly less than the size of S? Yeah, Abhinav.
So if we consider the set S minus R, then there exists a bijection from S to NS. So
Absolutely.
their sizes must be equal.
Absolutely. Absolutely. You're right.
So then
Yeah. So basically,
one
if somebody belongs to NS, what does that mean? So there exists an alternating path from R to V, right? But then V must be matched to somebody in V1, and that guy must belong to S, right? So now what do you want to claim? Right. So let us copy this statement on the next slide. So we have proved this, and now it's time to use it. Right. So this has been proved on the last slide. And now the next claim I'm going to make is size of NS is strictly less than size of S. Right. So what is the idea? The idea is essentially the same. It's just playing around with alternating paths, right? So if I have this V2, this NS, right? So this is NS, and if I have some V in this NS, right? So this is V1, and this is R, right? So note that by definition R is in S. This is S. Right, so V is in NS. What does that mean? So then it means that there exists some alternating path from R to V. Right, that's what this claim tells us. Right, so it could be something like this. Or maybe I'm swapping the colors. Let me just stay consistent with the colors. So what colors did I use in the previous slide? Acha, so blue for non-matching edges, pink for matching edges. Okay, chalo. Right. So blue for non-matching edges. And pink for the matching edges. Right, so there exists some alternating path from R to V in that case. Okay, but now what? Now can V be unmatched? Can V be unmatched?
No,
No,
sir.
sir.
Because augmenting path.
Because otherwise this will be an augmenting path, contradiction. So V must be matched to somebody in V1, right? So the partner of V, right? It must be in S by definition, right? Because I can extend this augmenting path to that partner. This alternating part to the partner, and therefore that partner must also be in S. Right, so let us write this down. Proof: if V is in NS, then there exists an alternating path from R to V, right? So V must be matched to some U in V1. Why? Because otherwise the alternating path from R to V is an augmenting path.
So you should be in S.
Yeah, we'll argue that it should be in S. For now, it's just in V1. Okay. So now what? So now, right? So appending U to the right. Again, you'll have the same condition that. Oh, you'll not have the same condition. Yeah, sorry. Appending U to the alternating path. Right, so you cannot be in this alternating path. Why? Because if you were to be in the alternating path, the previous vertex must be the partner of U. Right, so if some vertex in V1 is in an alternating path from R to, right, so is in an alternating path starting from R, then the previous vertex must be its partner. That's the only way to get into some vertex in V1. Right, so appending U to the alternating path from R to V gives an alternating path from R to U. Right, so therefore U is S. Right, so what are we saying? The partner of every, right, so everybody in NS has a partner and their partner is in S. I'm not saying that every neighbor of V is in S. Right, so you could potentially have lots of neighbors of V which are not in S. Why? Because obviously these are not the matching edges. Right, so the partner, the neighbor of every vertex in S is in NS by definition, and the partner of every vertex in NS is in S. Okay, understand the difference between neighbor and partner. Okay, cool. So now what? Right, so now, right, so what is S like? So S is equal to the set R union, right? So S contains, so S for every V in V2, V in N of S, S contains the partner of P. Right. Moreover, S also contains the unmatched vertex R.
So here, partner, we are referring to the vertex in V1 that matched to V from the maximum matching, right?
Yes. Yeah. So I'll write the clarification. Yes. So S also contains the unmatched vertex R. So by partner I mean the unique U such that UV is in M star. Right, so for every V in NS, V has a partner and it is in and it is in S. So let me write it that way. For every V in S, right? So every V in S has a partner and the partner is in S. Okay, so this is a bit cluttered. And the partner is in S. Okay, so everybody in NS has a partner and that partner is in S, and moreover S also contains the unmatched vertex R. So which means S contains one more at least. Right, so partner refers to the unique U such that UV is an M star. Right, so what does that mean? So therefore the size of S is strictly greater than the size of NS. Yeah, it was a bit involved proof, I believe. Right, so let me clarify here. We claim size of S is greater than size of NS. Yeah, and this result is called Hall's theorem. Okay, any questions? Any questions? Right, so I'm willing to wait even for a minute, because what we are going to do next is kind of completely unrelated with this bipartite matching. It's some another cool thing that I wanted to share with you, and that has something to do with trees. Right, so the plan is in this lecture. Yeah, Dhruv.
So can you show the previous slide for a second?
Sure.
So here you have written, let S subset of V1 be the set of vertices that are reachable by alternating paths starting from R. So sir, if and only if there exists any S, so basically we are constructing an S for the theorem.
Yes. In particular, R itself is an S.
And sir, how have we defined NS?
So NS is the set of neighborhood, the way we have defined it over here. NS is this notation, the set of neighbors of some vertex in S. That's all.
Okay, sir. So basically, we are constructing both S and NS.
Yeah.
So, but we are assuming that M star already exists.
Right. Why can't we assume that? There exists some maximum size matching, no? Look at all the set of all matchings, pick the one with the maximum size. The set of all matchings is finite.
Yes, sir.
Right, so pick one with the maximum size. There could be several, out of them pick anybody. Pick an arbitrary matching. If there are several matchings of maximum size.
Okay, sir. Got it. Thank you.
All right, cool. So should we move on to something new?
So like in a path, is a zero length path defined?
Sorry, I couldn't hear you, Gurarman.
Sir, I was saying that is like one vertex path. Is a path containing only one vertex defined?
Yeah, what is a path, right? It's a sequence of vertices, right? Where every pair of adjacent vertices is adjacent, it has an edge. Right, so in particular, single vertex is a path.
Okay.
Right, so if that is not clear, maybe I should write with a set of vertices that are reachable from by alternating paths starting from R and including R. Let me make it explicit if you like. Okay. Right, so a single vertex alternating path might not make sense. So maybe it's best to include R in this set explicitly. Yeah.
Should we? Yeah. Sir, I have a doubt. In the claim on this page, we have said that the neighborhood of S is equivalent to the set of all the vertices which are reachable from R, right?
By alternating paths. And which are in V2. Right, so the vertex should be in V2 and it should be reachable by alternating path from R. That's what the right hand side is in this case.
So we are saying that in any graph, in any bipartite graph, there will for some R there will be an alternating path to every other vertex on the other side. Like.
No, that's not what I'm saying. If there is an alternating path to some V, then I'm included in this set. So this could be possibly a strict subset of V2, possibly. Okay.
But neighborhood of S is any vertex in V2, right? That has an edge.
Correct. And I'm claiming that the neighborhood of S is precisely this set.
Okay. Okay.
Right. That is the claim. Okay.
Sir, can't we just construct a set S that has the vertex R and any arbitrary collection from V1? Then because it is a matching, the other part, the V1, the arbitrary part will be matched to.
The problem is you're talking about neighborhoods, no? Right? So you could have a case where right, so let's see whether your construction works. You have this V1, you have V2, so R is unmatched, so you want to include R and take some arbitrary set, right? Is that what you're saying?
Yes, sir.
Right. So now the problem is you could have this kind of situation, right? So some things over here are kind of unmatched, so all of that is in N of S. So why do you have the guarantee that its neighborhood is smaller than itself? Right. So because you are taking all possible blue edges, and then to come back you are taking, right? So there are some pink edges, but they could be like this. Right. That is the problem. It could very well be the case that the partners of these NS guys are outside S, which is why your S is too small. Okay.
All right, sir. Thank you.
That is the critical property that we use to argue that S is at least as large as NS. Right? We said that you take any vertex in NS, its partner must be in S. If that property is violated, then we can never guarantee that the size of S is more than the size of NS. Okay, so which is why we did this specific construction. By our construction, we ensured that S contains all the partners of everybody in its neighborhood. Okay.
Yes, sir. Thank you.
Okay, so for that matter, if I take any S in S subset of V1 which satisfies this property, what property? That the S contains the partners of everybody in the neighborhood of S. I take any such set, that set is guaranteed to have size strictly larger than the neighborhood, assuming it includes some unmatched vertex also. Okay. Let's delete this slide. So should we move on to something new now?
Sir, I have another doubt regarding this. So suppose our maximum matching are the only edges that we have in the graph, and then we have one unmatched edge, unmatched vertex R. Then our NS is not equal to the all the points which are reachable from R, right? By alternating paths.
What is NS then?
In NS, it is empty, right?
It is empty, but that is also equal to the set of points in V2 which are reachable by alternating paths from R.
No, like NS by the original definition are those 4 points, right?
Wait. So is this your graph? Is this your entire graph? Is
yes.
That what you're talking about? Okay. So now what is so suppose S, right? So what is S now in this case? What is S in this case?
S
only R.
R, only R. What is NS? What is NS by the definition of NS?
Empty set.
Empty.
Okay. I was thinking S is the entire set V1. That was.
Oh.
Okay.
Oh, no.
Yeah. Okay. Got it.
Okay, cool. Fine. So we are moving to something completely different because I thought that would be a cool thing to share with you. Right. So our goal is the following, right? We want to count the number of trees that are possible over a given vertex set. An extremely very basic question. right? So the question, I actually, by the way, you might have noticed that I have also included this question in the tutorial. I was hoping that some of you will at least try it out before we start discussing, but let's see, right? So question, right? So given a finite set S, what is the number of trees over the vertex set S? Okay, so simple example. So if, right, so obviously this depends only on the size of S, right? The identities of the vertices really doesn't matter, right? So example, if size of S is equal to 1, then one tree, obviously the single vertex. If size of S is equal to 2, then still you have one tree, which is just the edge. Size of S is equal to 3. How many trees do you have? Let's see, you have three trees. Why? Because you have three vertices A, B, C. The tree must really look like a path.
Yes.
There is not a choice. And then there are three possibilities for the middle vertex, right? So you have three. What if size of S is equal to 4? Sorry?
16.
6 trees. Why do you say 6?
16.
16. Acha, 16. How did you get that?
So like there will be those in which there is a vertex having degree 3.
Sorry?
And then the other one in which there are two vertices having degree 2, and there will be two having degree 1.
Oh, so you're okay. So you have okay. You're talking about trees which are kind of have this structure, and then there are other trees which have this structure. Is that what you're trying to say?
Yes, sir.
Yeah. So how many trees of this type do you have?
12.
12. And why is that so? That is just 4 factorial by 2, right? So you can label these vertices by A, B, C, D in 4 factorial ways. But then if you kind of just flip it around, you still get the same tree. So you are dividing by 2. And similarly, there are four trees of this type. Why? Because you have 4 choices of what should be this guy. Okay, so yeah, let's see. So raise your hand if it is not clear why you have 12 trees of this form over 4 vertices. And feel free to raise. I mean, yeah, there's nothing wrong if you have not understood. Okay, so apparently people have understood. So cool. So you have, if size of S is 4, then you have.
Can you repeat the counting method again? Like how did you count that 4 factorial by 2?
Okay, so let us look at trees which have this kind of a path structure. Right, you have 4 vertices. How many ways are there to label the 4 vertices? 4 factorial. But then I'm saying that if this tree A, B, C, D is same as this tree, D, C, B.
Yeah, okay, sir, understood.
Okay, so which is why I divided it by 2, right? So there are kind of two ways of labeling which give you the same tree. And there's no such question over here. So well, so for size of S equal to 4, you have 16 trees. What about 5? So what we are planning to do is we'll just do this by brute force for some small values, may not, yeah, possibly not even 6. We'll just stop at 5, and then we'll come up with a conjecture, right? So if you have size of S is equal to n, how many trees do you have? Right, so we'll come up with a conjecture and then we'll try to prove it. Right, so what if size of S is 5? How many trees do you have? Maybe take a couple of minutes to think and then let us know, let everybody know. Yeah, if you're watching this offline, you're not in the live class, then maybe you should either think for 2 minutes and then we'll be back in the lecture, or maybe you could skip a minute or two if you are watching this video. Yes, Abhinav?
So shall I say the answer?
Oh, you're already ready. So let's wait for a minute or so, right? So by that time, more people will be ready with the answer, and people who might be watching this offline, they would have skipped, right? So let's wait for a minute or so. Right, so what is the pattern? We'll look at all possible structures, the unlabeled trees. How many structures do you have? And then for each structure, we'll count the number of labelings that is possible. Okay, that's what we did for any size of S being equal to 4. And yeah, that's the plan for S equal to 5 also, size of S. Yeah, so actually, if you have an answer, just keep your hand raised so that I know how many of you have an answer. Okay, so some people do have an answer now. So Abhinav, yes, what is your idea? How do you count?
So first of all, we have, like we did for 4, we have a linear structure for 5.
Sorry, linear structure. Okay.
Yeah.
Let's
so
draw
that will
all
be having.
structures.
So this
Yeah,
has 5 factorial by 2. So, like we match A, B, C, D, E, and then it is 5 factorial by 2. Then we have 1,
which is
3
what,
at the
60, no?
second.
What was
this
this?
is 60.
60. Okay.
Then we have 4 vertices in a line, and the fifth one is attached to any one, second or third. Yes, here. So this has, let's say, A, B, C, D, E. Then D and E. These two are similar. So again, we have 5 factorial by 2.
D, E. Yeah. So what you are saying is these two can be swapped and still the labeling is the same. So even in this case, you have 5 factorial by 2, which is 60. Okay, go on.
Again, now we have 3 vertices in a line, and then 2 of them in the middle.
So it's a star. So called star graph. Okay.
Yes.
Now these are
we
just
have 5 possibilities.
5.
Only
So
choosing the middle one. So this is 125.
Total is 125. Okay. So raise your hand. Okay. Yeah. So people who have an answer, could they lower their hands, please? Okay. Raise your hand if this calculation is not clear. Okay. So this calculation seems to be clear. Okay. So now any conjecture, what should it be for an arbitrary n?
N to the power n minus 2.
N to the power?
N minus 2.
And who is this? Chinmay is saying n to the power n minus 2. Okay. Is this a conjecture or you knew this result already?
And I was looking at the pattern, like all of them are squares or cubes. So
which means it's a conjecture. Okay. Right. So this is 1 to the power minus 1, 2 to the power 0, 3 to the power 1, 4 to the power 2, 5 to the power 3. So Chinmay's conjecture is this: for if your size of S is n, then this must be n to the power n minus 2. Is everybody with me up to this point? Is it clear what we are trying to do? Okay. So Chinmay, your guess is right, and we are going to prove this. Okay, so we are going to prove that. So let's make that claim. Let's write down the claim over here. The number of trees over a finite set S of vertices is size of S to the power size of S minus 2. Okay, and how are we going to prove this claim, right? So let's look at the very high level idea of this proof, right? So this is the set of trees, and this some other set, right? So we'll prove that there actually exists a nice bijection between these. What does that mean? It means that the number of trees is equal to the size of this other set also. But this other set that we construct is going to have such a nice structure that it's extremely trivial to prove that its size is n to the power n minus 2. Okay, and that is the way we'll conclude that the number of trees is equal to n to the power n minus 2. Okay, so what should this set be? What is the trivial set whose size is, I mean, yeah, there are obviously tons of trivial sets whose size is n to the n minus 2. But can you give some easy structure that comes to your mind just looking at the number n to the power n minus 2? What should this set be? Any guess, Vedant?
So maybe it's a array of n elements where each element has n minus 2 options, like n minus 2.
Array of n elements where each element has n minus 2 options. Does any objections against this from the class?
Opposite. Minus
Opposite.
2 elements.
So opposite.
Opposite. Yes, absolutely. You're right. Right. So this is the set of arrays of right. So arrays of size what? N minus 2. Each element being an element of out of a set of sizes. But what set of sizes do we set of size n do we have? We have already S, right? So each element being an element of each entry being an element of S. Let me put it that way. Being an element of S. Right? So you have on one side you have the set of trees over the vertex set S, and on the other side you have arrays of size n minus 2 where each entry is a vertex, and that's it. That's otherwise there is no constraint. This is the set we are looking at, and we want to prove that there is some nice bijection between these two sets. The size of this latter, the second set, is n to the n minus 2, n to the power n minus 2 obviously, and therefore the number of trees is going to be n to the power n minus 2. That is the plan. Okay. Cool. Yes, Shrimanti.
Sir, when we say set of arrays of size n by 2, what kind of trees do we mean? Like each element, we are not choosing vertex, right? What were we choosing? So when we are saying set of arrays of size n by 2, each element being an element of S, so what kind of tree are we constructing?
So we'll see that. We'll see that. Just understand the two sets for now. We'll see the bijection between them. Don't worry. It's not so easy that I can explain it in a minute. Okay, so it's a bit involved. We are going to see it. Okay, so how do you convert a tree into an array? How do you convert an array into a tree, right? And then we'll have to prove that if you convert a tree into an array and back into a tree, you'll get back the same tree, right? So all these things we'll have to worry about. Abhinav?
So these elements are distinct, right? Of each array, or can they be similar?
Not necessarily. No. I have not said that. I have not said that. Otherwise, the size is not going to be n to the n minus 2, no?
No. In a single array, the elements are distinct, or can they be same?
That's what I'm saying. They need not be distinct. If you are trying to count arrays which have distinct elements, then that number of such arrays is not going to be n to the n minus 2. Right?
So let's say we have an array of 2 elements. S is 4, 1, 2, 3, 4. Then can this array contain 1, comma 1?
Yes, it can. It can. That's what I'm saying. I'm going to count these, which is why I'm getting the number n to the n minus 2. Otherwise, it will be some np something. No, np n minus 2 or something.
Oh, okay. Sorry. Yes.
Okay. Yeah. Cool. So now let us see what is this bijection? Let us first understand, right? So, okay, let's not call it a bijection. It's some function from this set to this set of trees to set of arrays. We'll define that function properly first, and then we'll worry about proving that it's a bijection. So for this lecture, we'll just define the function and just get an intuitive idea of what that function is doing. And maybe in the next lecture, we'll prove that it's actually a bijection. Okay, and so this right. So if you have a tree over here, then the array which this tree gets mapped to is called the Prufer sequence of T. Right. So the array which T gets mapped to is called the Prufer sequence. Prufer sequence of T. And we'll see how do you get the Prufer sequence.
So like, would it be somewhat related that it would have at least 2 leaves? So like we exclude those and like somehow specify the neighbors of others, something like that.
Sorry, say that again.
So like the size of the arrays, like we have taken n-2. So is it somewhat related that the tree would have at least 2 leaves?
It's not related to that actually. It's related to the fact that if you have a vertex set of size 2, then you just get one tree. So remember, yeah, if n is equal to 2, then remember this set of trees is just one singleton set. And now we are looking at arrays of size 0, each element being being one of the two values. How many arrays of size 0 do you have? Just one array, the empty array.
Okay.
Okay, so that is like the extreme case. Okay, cool. Right. So how do you construct a Prufer sequence of a tree? So we are looking at Prufer sequences of trees. Okay, so for this we'll assume, right? So we'll make a small assumption that our vertex set, right? So assume S is a subset of natural numbers. Okay, that's a minor assumption to define this Prufer sequence in a consistent manner. That's all. Right? Even if your vertex set is not really a set of natural numbers, that's not a big deal. You can easily fix that problem once I define this Prufer sequence. Right? So for now, let us just assume that S is a finite subset of natural numbers, and let's assume that size of S is at least 2. Right? So we'll make this size of S being 1. This is a special case where all this stuff is not really applicable. Right? So whatever we are doing, this Prufer sequence business is applicable as long as your size of set is at least 2. Okay, so this is a special case. Right, so S is a finite subset of natural numbers. Right, so yeah, obviously we are taking that as a vertex set of something, so which means S finite. Okay, so how do you construct the Prufer sequence of a tree? Let's take an example of a tree, maybe. Let's draw some random tree. How many vertices do we have? So let's label the vertices something, right? So let's label the vertices. Let us call this 1, maybe this is 2, this is 3, this is 4, this is 5, 6, 7, 8, 9, 10, and 11. Okay, 11 vertices. And now somehow we want to convert this 11 vertex tree into an array of size 9, where every entry is one of, right? So we want to convert this into an array with 9 elements, 9 entries, each coming from the set from the set 1 through 11. Right, so that is what we are looking for. So how do we construct this array? So we do the following, right? Every time we find the leaf node which has the minimum label. So which is the leaf node which has a minimum label over here? 3 is the leaf node which has a minimum label. Okay, we delete that leaf and its associated edge, and we record the unique neighbor of that leaf. Okay, so let me repeat the process once again. Right, so the idea is the following. repeatedly find leaf X with minimum label, record its neighbor say Y, and then delete leaf X and edge XY. This is what we'll do repeatedly. Right, so the leaf with the minimum label is 3 in this case. So we'll record to construct this prefer sequence of right. So this is T, and now we are constructing the prefer sequence of T. Right. So what do you do? So you 3 is the leaf with the minimum label. Right, so what is its neighbor? Its neighbor is 5, so we'll record 5, and then we'll delete 3 from the tree. And you continue, right? So now what comes next? Does somebody want to continue this? What is the minimum, the leaf with minimum label? It's 4 now.
4.
Yeah, so it's the neighbor of 4 is 5, so I'll write a 5 once again, and I'll delete this 4. What next?
7.
7 is the leaf with the minimum label. That is true, but what should I record over here?
1.
1 and delete the 7. Yeah, 1. This is 1.
Another 1.
Another 1, and what should I delete? 8, right?
Yes.
Yeah, now what?
6.
6. Record a 6, delete 9. Okay. Now
2.
2 and delete
6.
6. Right. So remember, 6 now has become a leaf node because we deleted 9. Good. Now what remains?
10.
Yes. Yeah, that's it, right? 10. Yeah, 10. And then I recorded 2. Cool. Yeah. So one thing I forgot to mention over here. So you keep on repeating until 2 vertices remain, and therefore 1 edge remain. Okay. Yeah. So 10. Yeah. You recorded a 2 and you deleted 10. Then what next? Now
we will delete.
Sorry.
We will delete 2 now.
And record 5. Okay, so record 5, delete 2. Next.
Delete 5.
Delete 5.
Yeah,
Record 1.
delete 5, record 1, right? Record 1 and delete 5, and that's it, because now you just have 2 vertices, 1 and 11. Okay, so this is the way you construct a prefer sequence of a tree, right? So we need to prove a lot of things. We need to prove that right, this is a bijection. Well, that is the most important thing that we need to prove. What does that amount to prove? It amounts to proving that given a sequence of length size of s minus 2 with elements coming from S, right? First of all, it should have a pre-image, and then secondly, we should prove that it has a unique pre-image, right? So we want to prove that this function mapping a tree to prefer sequence. First of all, we want to prove that it's a surjection, which means that every sequence has a pre-image, right? And then we want to prove that it's also an injection, which amounts to saying that you cannot have 2 trees who have the same prefer sequence. Okay, so for every sequence, we want to prove that there exists a unique tree whose prefer sequence is the given sequence. Okay, so that we'll do in the next class, but let's try the reverse process, right? So suppose I give you S and I give you a prefer sequence of some tree. Can you actually construct a tree? Okay, so okay, let's do that. So let's say my S is let's say my S is the set 0 to 9, and let's say my sequence is 1 5 9 7 9 1. What length do I need? I need a sequence of length 8, right? 0 2 1, let's say. So no, this is one more than what I needed. 15979102. Okay, so yeah. Okay, so this is the prefer sequence of some tree. Now let us understand what are the properties of that tree. Question: what are the leaf nodes of this tree? So this is a prefer sequence of tree. Is a prefer sequence is the prefer sequence of tree T. Okay, so question: what are the leaf nodes of tree T? Yeah, Dhruv?
So at every step we are deleting the leaf node which has the smallest value. And
Correct.
so at every point there exist at least 2 leaf nodes.
Okay.
So we cannot delete 9 at any point of time.
You cannot delete 9 at any point of time. Good point. Okay. So what?
So then how can this be a proof of sequence? Because we cannot delete
But
9.
what are we recording? What are we recording? We are not recording what you deleted. You are recording its neighbor.
Sorry, sir.
Okay. Yeah, it's okay. It's okay. Right. So my question is, what are the leaf nodes in this tree? Any good guess to that?
So like except 2, I think anything that doesn't come in this sequence should be a leaf node.
Anything that doesn't come in this sequence should be a leaf node, but why except 2?
So because at the end, like if we have a tree of size 3, then maybe there is a leaf that comes in this.
No, but
Oh,
what is so special about the vertex 2?
No,
Ramanuj? Yeah, you're almost right. Ramanuj?
I don't. Well, 2 was the vertex in, like, there was a neighbor to 2, so I don't think 2 is also a leaf node. So I think except for 9, we can't say anything for 9 here. We can say that the first vertex deleted was a 3, I guess.
Correct.
Because 1 and 2 and 0 are already in the sequence, so there was something connected to them, and
Correct.
they were connected to a leaf.
No, that's fine. So then how do you determine the leaf set of this? What is the set of leaves?
Anything except for wait, I think I don't know about 9, but anything that isn't in the sequence should be a leaf then.
Yes, you're almost right. Divyanshu?
Yeah, I was also saying something like Raman, like the vertices that are not there, like 3, 4, 6, 8. So out of these, like I think some 3 would be, and like the first one we can determine like 3, because
No, but I want to determine all the leaves of this tree in one shot. Let's say easily I can do that.
Okay, sir.
Right. So is it ever possible that you'll record a leaf node in this sequence? Right. It's never
But
possible.
the leaf node won't be connected to some other leaf, right? So it can't be.
Exactly. So you will never record a leaf node in this sequence. That is the observation. Okay, so the answer to this question is, what are the leaf nodes? 0, 1, 2 is there. So 3, 4, 5 is there. 6, 7, 8 is not there, and 9. So these are the leaf nodes. Okay, so next time we'll continue this further and we'll try to construct the tree from this prefer sequence, and then we'll prove the bijection property. All right, so that's all for today. See you on Monday.